Okay, so when we get into velocity, this is the first time you can kind of talk about relative motion. If you ever heard the phrase, everything's relative, that's kind of the truth. Think about this. If you have been on the freeway and say you are passing a car that's going in the same direction as you, does it seem like that car is moving really slowly? Or say another car is passing you, all right? And you guys are both moving in the same direction on the freeway. It appears to happen slowly. But say, the car passing you is going 70 miles per hour. Now, what if that car was all of a sudden on the other side of the freeway, going in the other direction? Would they appear to be going just as slowly? Or would they seem to be going much faster? Because they're going in the opposite direction. Yet, they're still going 70 miles per hour. All right? All motion is relative. It's based on your point of view and the directions that things are going. So we need to address that idea. So, think about this. What is the speed of your desk, or the chair you're sitting in right now, or the desk, or whatever your computer or phone is on top of at the moment? What is its speed? Think about it for a second. All right. Odds are most of you are probably saying 0. It's not moving. All right. But think about this. The Earth is moving at 500 meters per second about the equator. So aren't you and your desk and your chair and whatever you're watching this video on moving at 500 meters per second too? Or say the Earth revolving around the sun, that's moving at 30,000 meters per second. Or the solar system, it moves too at another speed. So it all depends on where you're looking at it from, right? You sitting on Earth, not looking at it from, say, the outer space and actually seeing Earth moving, think it's not moving at all. But someone in outer space, if they were to, say, zoom in on your phone, it'd be going really, really fast. Okay? So, all velocities, any kind of motion, it's all relative to your point of view. So your frame of reference is essentially your point of view. It's the physics way of saying your point of view. All right? So it's based on where you are. All right? So if you say, the frame of reference looking at, if you talk about the brown guy looking at the blue guy, his frame of reference is going to be different than, say, the red ball looking at the blue guy. And what you're observing will be a little bit different. What do you think the most common frame of reference is that we use? All right. If you can't think of something off the bat, I highly suggest this video. It's a really old school, the video is probably older than you and I combined, but it's a really, really good video, really low-key, easy ways of kind of drilling this into your head if it's not quite matching, giving you a visual of what's going on as far as frame of reference. All right. And it will also tell you that the most common frame of reference is Earth's surface, all right, the ground. That's usually what we compare movement to, because we treat the ground as not moving, so everything is moving on the ground, all right, or the Earth as not moving, even though it is, but we can't see it, so relative to us, it's not moving. So, most common frame of reference is the Earth's surface, or the ground, or the Earth, okay? Not outer space, not you, it's the Earth. Okay? So let's start applying that to some information. Make this a little smaller. We're going to use this idea for a few seconds. Those of you that have been to, trying to think if Sky Harbor actually has one of these. But if you've ever been to the Atlanta airport or the Tampa airport, or a lot of them, they have these funny little walkways that get you through there a little faster. All right? So consider this walkway for the rest of the problems moving north at 2 meters per second. All right, so remember that. The walkway itself is moving north at 2 meters per second. So here's a few questions. What is your velocity relative to the ground, which is not moving? All right, if you are also walking north at 3 meters per second. So let's make this a little smaller. Again, good idea is to draw pictures. All right, So, what we know for sure is we have the walkway moving north. All right. At 2 meters per second. And then we are also going to have you walking on the walkway at 3 meters per second. So what we're going to do is we're going to take our two vectors and we're going to add them together, which means we have to set them up head to tail. So we have 3 meters per second. Okay. Those are set up head to tail. So that means our new vector is starting all the way down here. Let me make this a different color. And going all the way up here. What do you think that is added together? I hope you are saying 5 meters per second, and then all of these, because their velocities, should have norths on them. Alright, so this one is 5 meters per second north. Let's try this again. I didn't really need to re-erase that one, but now we're going to go the other direction. Alright, so here is our 3 meters per second north. Or sorry, our 2 meters per second north. But we need to draw your motion going 3 meters per second south. Alright, so I start this arrow up here because they have to be set up head to tail. Alright, so then if you think about the vector that is left, if this is our open tail, if you remember the vector packet, this was kind of what you were doing a bunch of times. And there's our open head. So this little vector right here, let's write this one in. This is 3 meters per second south. How big do you think that is? Alright, so we're canceling out the 2 meters per second, leaving 1 meter per second left over, and the direction is south. Alright, so it's kind of like if you go on there in the wrong direction, you have to go faster than the walkway is to actually get anywhere. Okay? So, let's do another one. Alright, so this time, again, we are walking south, but not quite so fast. We're only going at 1 meter per second south. Alright, so resultant is drawn from the open tail to the open head. Alright, so what size is that going to be? Hopefully you're seeing that the 1 meter per second is being canceled out, and what's left of 2 is 1 meter per second. And what direction are you going this time? So, are you going fast enough in the opposite direction to actually get anywhere? No. Alright. So, one more. Let's see. Sorry, I've been writing these in. 1 meter per second north. And this one was 1 meter per second south. So, just keep in mind, you gotta draw pictures for these things. Otherwise, you're gonna get lost with all the directions and numbers and what cancels and what doesn't. The picture helps make it really clear. So the last one with this walkway, here is our 2 meters per second north, and now we are going to walk south at 2 meters per second. So, again, setting it up head to tail. And so, if the walkway is moving you 2 meters per second south or north, and you are moving 2 meters per second south, those cancel out. Are you going to go anywhere? Hopefully you are saying no. So this gives you 0 meters per second. And if there is no velocity, you don't have to give a direction because obviously you're not moving. Alright, to another sort of situation. Got planes. Alright. So, there's a couple of terms you want to know in regards to planes. A tailwind is a wind coming up behind the tail of a plane. This is my very bad drawing of a plane. Looks kind of more like a whale. But there's the plane, alright? And the plane is going in this direction. A tailwind will also go in that direction. Okay? So again, we can use these vectors to help us. So here's our plane's vector, and it's going, oops, gotta draw it south, sorry. Our plane is going south at 100 kilometers per hour. Alright, and it encounters a 25 kilometer tailwind. So tailwind, and this is 25 kilometer per hour tailwind. So even though it doesn't tell us it's south because it's a tailwind, we know it's going in the same direction as the plane. Alright, so our relative velocity is those two added together, which will be 125 kilometers per hour south. So the question is, what is the plane speed? That should say velocity relative to the ground, and how long will it take to fly 300 kilometers. So we just figured out the velocity, so now we need just to do that problem. So we know our velocity is 125 kilometers per hour, and we know that it's going to go 300 kilometers based on the units. That is our displacement. Alright, so we have this handy-dandy equation is change in s divided by t, but we want to know time, so rearranging that, you get change in s divided by velocity. Alright, so we're going to plug that in, and we will get 300 kilometers per hour. Nope, I'm plugging it in wrong. Hopefully you caught that before I did. So we need our display. Oh wait, I was just writing my units wrong. Sorry about that. 300 kilometers over 125 kilometers per hour, which is going to be 2 point something. Let me grab a calculator. Sorry about this. 300 divided by 125. 2.4. Then if you look at the units, the kilometers cancel out and we have hours left. Okay? So, this is not only finding your new relative velocity, but also now applying it to a problem. So, is want to just define what headwind is. So if a tailwind went in the same direction as the plane, a headwind goes in the opposite direction. Alright, so if our plane, that is a really bad looking plane this time, but if it's going in this direction, the tailwind will be going in the opposite direction. Alright? So this time we have our 100 kilometers per hour south, but we have 25 kilometers per hour north because it is a tailwind. Alright, so we're going to find the velocity. Sorry about that. So our resultant is going to go from the open tail to the open head. So we're going to have 100 minus 25, or 75 kilometers per hour south. Alright, so let's list out what we know. Our velocity is 75 kilometers per hour south. Our displacement is again going to be 300 kilometers. Alright, so our equations look the same as last time. Velocity equals displacement divided by time. Time is equal to displacement divided by velocity. But this time our substitutions are slightly different. 300 kilometers over over 75 kilometers per hour. Alright. So we solved that, and this time it's going to take a lot more time. It's going to take 4 hours. Okay? So that's the end of the video. If you need to, rewatch some of these equations, because you will have to at least do this part in the questions. And you never know, I might throw one of these on your quiz tomorrow. So, have the online assignment and notes ready for class tomorrow. Bye.